Assalamu alaikum wa rahmatullahi wa barakatuh. We return back to a next video that we will discuss another procedure which is called combination. We will notice that when there is when the order is not important, we will use another procedure called combination. There are many problems in which we are interested in determining a number of ways in which R has been taken, selected from among n distinct objects without regarding to the order. Which means that this is an important condition without regarding to the order. Then such selection is called combination. Suppose here in the example 14, in how many different ways can a person gathering data from a market reason organization select 3 of 20 households living in the certain apartment complex. Since here number of ways equal, since there is no order, then you will choose n out of R, which is 20 out of 3. Here it will be opened like this: n factorial over R factorial n minus R factorial. Notice R must be less than or equal to n. It cannot be greater than n. Then 20 factorial over 3 factorial, 17 factorial, 20 minus 3. Here we have it like this. Actually, combination means the same as subset, and when we ask for the number of combinations of R objects selected from a set of n distinct objects, we are simply asked for a total number of subsets of R objects that can be selected from a set of n distinct objects. In general, there are R permutations of the objects in a subset of R objects, so that NBR permutation of R will be divided by R factorial. This is why we put this in theorem 1.7. The number of combinations of n distinct object taken R at that time is like this: n over R, n factorial over R factorial, multiplied by n minus R factorial, where R cannot be greater than n, 0, 1, 2, up to n. This is important. See the next here. Example number 115. In how many different ways can 6 tosses of a coin yield 2 heads and 4 tails? You know that every coin عملة, has 2 faces, 1 head, 1 tail. Here you have, in order to choose, since the order is not important, you will write 6 over 2 will be the same as 6 over 4. They will give you the same answer. This is why I write this. Here, suppose that we have here this example. In how many different committees of 2 chemists, 1 physics can be formed from 4 chemists and the 3 physics on a faculty of a small college. First of all, number of chemists 4 over 2, which is 4 factorial over 2 factorial, 4 minus 2, 2 factorial. It will be 4 by 3 over 2, which is 6 ways. Another thing, in order to choose physics, it will be 1 from 3. It will be 3 factorial over 1 factorial في 2 factorial, which is 3 ways. Total way, it will be 6 by 3, it will be 18 ways. Total. We will continue now. Sorry for there is a problem in the iPad. Here we will continue. Partitions like this, يعني here combinations of R objects selected from a set of n distinct objects may be considered a partition of n objects into 2 subsets containing, like the previous example. You divide it into 2 for physics or chemistry, or you can solve it at the same time. 4 over 2 multiplied by 3 over 1. Multiplied by 3 over 1, it will be 18 ways. This is number of ways. If you like, in one step, you can do it. Here, we will move to the approximately next to the last theorem, which is theorem 1.8, the number. Suppose we can write the previous theorem, theorem 1.6. You can write it in another way, the same as theorem 1.6, the same, but you can write it in another way. The number of ways in which a set of n distinct objects can be partitioned into k subsets, with n1 objects and in the first subset, n2 objects in the second, and so on. Notice you will have n equal n1 plus n2. You must have the same condition. This is why we write it n over n1 into until nk equal n factorial over n1 factorial into factorial and so on. The proof is not with you, and this is why here, this example, in how many ways can 7 men attending a convention be assigned to a 1 triple, means 3, and 2 double, hotel room 2. Look, when you make addition, 3 plus 2 plus 2, yani you have n total n7, n1 equal 2, n2 equal 3, n3 equal 2. 2. If you make the addition, it will be 7. Then you will use theorem like this. Write it 7 over 3 factorial, 2 factorial, 2 factorial, or write it 7 over 3, 2, 2, and so on. The same answer. This section is not for you, with you, and all the section proves they all not with you. We will now finish, but we will have to solve some questions about the previous material that we have it here. Here, in how many ways can 5 persons line up to get a bus? Since the order is important, then you will have order is important. Then number of ways means in factorial, which is 5 factorial equal 5 by 4 by 3 by 2 by 1, 6, 120 ways. Here, question number 38. Question number 38. In how many ways can 8 persons form a circle? Order is important. Then, number of ways for a circular equal n minus 1 factorial, which means that 8 minus 1 factorial equals 7 factorial. We don't need the last answer. Here, how many permutations are there on the letters in the word great? Solution. Notice here, A, the word great has no repetition and total number of letters 5. Then you can solve it in many ways. And here, number of ways equal n factorial, which is 5 factorial, which is 120 ways. Or solve it like B. B, we have different great. Then total number of letters 5. N1 equal G, which is 1, N2 R 1, N3 E, which is 2, N4 equal 1 اللي هي T. Since the total since great, since total sum equal 5, 1 plus 1 2, 2 plus 2 4, plus 1 5, then use the number of ways permutations equal n factorial over n1. I will see the space